So we had finished two of the op-amp circuits. That was running battery, and then the inverter. The inverter ended up being the voltage follower. When we got this other non-inverting part, inverting part, and we had this one. Was this one grounded? And then this was, we were able to get the V out. V out was equal to V in. Just to confirm the thing so that the V in was at the this place here, brown point here, and because of the assumption that VB equal to Vn minus Vb, and then Vb was equal to V out over AD, and AD was approximately infinity, and then this was equal to 0, and we get it as a rule that Vn is equal to V for an ideal amplifier. So we get the summing up. The summing So these days when everything I'm doing gets smooth, I sit back and first evaluate and think twice. But I read a book which gave me some courage that what you think is what you get. I would be in a jam and I'm like, I hope this border guy doesn't scratch me. I don't know him. And before I know, I've already scratched, he has already scratched me or I've already bumped into him. And so these days when something strange in my head comes up, I say smooth. And I forget what I was thinking and everything goes smooth. So I'm living a smooth life. If it rains in the morning and I'm scared of how I'm going to get out of the gate because of when I say smooth, it slows down, I go out. And once I'm in the vehicle, it rains like cats and dogs again, and I reach here. When I've arrived, the power is off, I say smooth. Friday wasn't... Friday I was busy with other things before the time, so I didn't have time to say smooth. But when I was going home, when I left the office after pulling out of the parking, I'm told that it came immediately. I only saw it when I reached the studio. But I said I cannot go back to the office. So we have a couple of inputs. We have V1 through R1. We have V2 through R2. We have V3 through R3. And these three are being fed through. So I can take this So we have, this is a summing amplifier. So we have V1, I1, V2, I2, V3, I3. Yes. And all of them are being fed here. So this is the inverting terminal here, Vn. And then we have the non-inverting terminal here at V, ground. And this is IF. We use the node at V at N. If I say Vn, that is fine. At the node at the non-inverting here at N. So we have I1 plus I2 plus I3 plus IF gives you. This is an ideal operational amplifier. Nothing goes in, nothing gets out. So nothing is going away from here, meaning that everything is good. So I1 plus I2 plus I3 plus IF equals to, this is at node N, this N here. That's the voltage N. Vn is there, but maybe for purposes of having our life easy, we name this one P and N in terms of these nodes. From Ohm's law, I1 equals to Vn minus, it is flowing this way, so it is V1 minus Vn over plus V2 minus Vn over R2 plus V3 minus Vn over R3 plus V out minus Vn over equals to 0.
So that's tantamount to saying that either we are not either, or say I1, I2, I3 are 0, or is it that some current is going to go the reverse direction? Maybe IF is going to be.
At the end of the day, IF is the best place that can help us to know where these I's can go. So if the feedback resistance, for example, if it was to be a variable resistor, or we choose the right amount of it, then part of it would be, we would have a flow going that side along with the feedback resistance. But the issue is that, like I told you that I needed to get a best way to explain this, is that we are putting in, already this one is not just a box, it's not like, it's not a box. I mean, it's not just a structure. We already are putting 12 plus here at 7 and 12 minus at 4. So it's already having things happening inside. So this is like a common emitter or common collector inside here. It is cookie. But we are not having anything going in or going out. And then we are having this feedback current depending on how much feedback we are sending back to this other side in order to determine what is going on. And this is a component which is, so it's like, this is not an isolated case. It's like when the way we do our our calculator calculations, when we are saying we are adding 1 plus 2 plus 3 equals, then it calculates and gives us an answer. So it gives us an answer after it has added all of these. So we are following rules, and only thing is that is helping us is that the assumption is that nothing is going inside this. So at this node, this plus this plus this plus this, which is also coming, are equal to 0. They are not 0, but they are being equal to 0 because nothing is going to go in the amplifier, but it can have an effect. These three can have an effect on how much is able to flow this backwards at the end of the day. Any other concern? I don't want to say grab this, summing up, this, no. I want us to have a feel together. But Vn equals to Vp, and because Vp has been grounded, so this will equal to 0. And this is because of the conditions which we talked of ideal of arm. For an ideal operation amplifier, and because this is the Vp equal to Vn, and the 0 came because Vp is grounded. So it means that I have V1 over R1 plus V2 over R2 plus V3 over R3 plus V out over RF equal to 0. And then we are interested in getting the V out. So V out will be equal to everything minus. So this is minus V1 over R1 plus V2 over R2 plus V3 over R3. And then we multiply by RF. If we had a bunch of them, which I forgot to do, so can we make some adjustments if we were having n of them? And so this becomes In, this becomes n. This one becomes Vn, and this is N, and this becomes N, and N, and then we do this. Just to make sure that we don't just we don't get accused as if we have an issue, a special relationship with 3. So if we have n of them, n inputs. So what would be the amplification? The amplification we wouldn't, as long as we have the output, then the amplification would have been over the output. So input over the output, but once we have the V out, we have no output. So V out equals to minus numbers on, in Netcom about this operation amplifier and chop them. There are answers there. Or even in here, in the profile. Let me see whether there is negative feedback. Just looking for where there is a number, a couple of numbers. Which you can do. Page 206. See. Page 206. General. You are big people, so I just tell you where things are. But I do what I'm supposed to do. Where is our green representative?
In the house.
Enjoying. I don't know. And people used to say that when it rains, you want to remain to cover yourself. When it rains, I feel uncomfortable. Even if it is a Saturday. I don't know where people get comfort when it is raining. It doesn't make me comfortable during the rain. Just want to check out. Okay, we go to the integrator. Integrator op-amp. Now, in electronics and electricity and magnetism, remember the difference between electricity and magnetism and electronics is that in electricity and magnetism, it's all about this guy, the charge. The charge is the big guy in electricity and magnetism. If this charge is stationary, we talk of electrostatics. If it starts moving, current electricity. If we look at the effect of this current electricity and how it is producing, what Orsted found out that when you put a wire through a cardboard and pour some iron filings, not iron fillings. Some of you call them iron fillings. These are filings. For us who grew up in the village, when you want to go to the garden, you file this part of the hole. Then you get some piece of grass and pass. If it cuts it without any problem, you know that now you have a sharp hole. Of course, that is for when you are going to dig in a place where there are no stones. Otherwise, if you make it too sharp, it becomes when it has when it is crooked like this. And if you are going for such a problematic land, you go with a forked hoe. It's the forked hoe you first put, and then you only use the hoe to scoop and do whatever way of digging. I'm sorry, I've understood nature that I have enjoyed life understanding nature. People in the central here, they go in the garden and just go digging and removing the grass and burn it. That's manure. For us, you dig, then you get this vegetation and put it here. Cover it, dig another part, so you keep doing that. So when your garden is done, there's nothing, no rubbish on the top. Everything is there as manure. And the guy will use his small piece of land The girls, when they are doing the filing of the nails, that stuff which gets off is what I call iron filings. So when Austin put these iron filings, this wire, they were able to form concentric circles. So we are from electrostatics, current electricity, to magnetism, and then when you move a conductor in a magnetic field, you create some current. So we go to electromagnetic induction by Faraday. When you make an organized effort to produce electricity by induction, then you get some alternating current from an alternating current generator. That's how it is. It's all about the charge, stationary moving thing. So it's moving, organized way of its motion, and then finally harnessing it. For us here now, we use this part of the current and see how it behaves being different. From the time we met here, we haven't done anything else other than knowing how current is moving in things. We looked at how it is moving in a resistor, in a capacitor, in an inductor, in a transformer, then we try to see, okay, how about these conductors, which sometimes decide to or not to. From there, then we said, how about now when we have used these semiconductors to make diodes, which allow or disallow, we transform diodes into transistors, which can now help us allow or not allow, eventually make them to allow and give us some amplification. Here we are now trying to make sure that we talk of when we have the op-amps in a very tiny configuration as an operation. So the reason I went this way in electricity and magnetism is that whether it is electricity and magnetism or electronics, when you see the word integrator, you should either in terms of the capacitor, inductor, or resistor, but mainly between these two. When you see an integrator, something should come to your mind. And most likely it's about this baby. If you look at the differentiator, if you see the word differentiator, something should come to your mind. Most likely the capacitor. And that's why you were being taught the mathematical methods in physics. That you are supposed to be having a circuit, and that circuit comes out with the differential equation or an integral, and then you understand how mathematics is helping you in the physics. So this, that's why I told you it could be this, it could be that. So the integrator is having a resistor at the input, and then we are having the, and then instead of the feedback resistor, we have the capacitance. So capacitance is related to the Q is equal to CV, charge from the I is equal to dQ dt. Then we have the charge being the same as I dt, and so the charge that we are interested in will be the integral of I, and hence the what in the integrator being associated with them. Whereas for the inductor, we talk of the V being the same as the induced EMF, which is the phi dt. And then, of course, whatever you put, still the voltage is being gotten by having the rate at which the flux is being linked with whatever we are using. So this is at the inverting, and then the non-inverting is grounded. And of course we have V out, C, so this will be, we shall call it IC, not the collector current, the current through the capacitor. And then since we have one resistor here, we have I, R, and this one we shall call it the resistance. Terms and conditions still apply. The VP is equal to Vn, VP is grounded, so that will be equal to 0. So this grounding here, VP. And then IR is equal to V in over R. I'm avoiding to repeat myself. And then IC is equal to V out over RC. Not RC. This is XC. And since I am going ahead of my time, I will say this is the same as C V out. So this would imply that V out is equal to, so I don't want to jump the step. The step is IR plus IC equals to IC plus IR equals to 0. And so we have V in over R plus VC dV out by dt equals to. Just want to know where I can be able to finish this, so that tomorrow we'll finish and this week we say bye-bye to op amps. So, or if we make V out the subject, then it will be the same as minus 1 over RC integral V in, and we shall take V in if it is varied with time to be that. The alternative circuit to this would be if we were to input our voltage through an inductor, and then we have if you are not good at drawing these things, you can draw an inductor like this. It's accepted. If you are very poor at drawing something like this, this works. Just help you have notes which are then you have your resistor there, V out, then you have R, this is the inductor here, inverting, non-inverting, and then the ground. And then as an exercise for this alternative circuit, try to show that V out is equal to the minus R over L integral V in T differentiation in a capacitor, there can also be integration in that same expression if you are looking for the other. And if it is the same in the inductor, there should be. If you have IC is equal to V out, if you chose to look for V out, you get an input on this side, much as this is a differential equation. I don't know whether it makes sense. I'm bringing it in this case of these two. This thing is, it's not complex. We are just stating the things of differentiator and whatever, and then you can do some example. It's like as if it is abstract.
Excuse me.
Yes.
So in the integrator circuit for the capacitor, I see it is a parallel kind of with the op-amp, and there is a resistance there.
I don't complicate matters. Here, instead we just replace the feed, what we have been using as the feedback resistor with the capacitor. And before we even think of the parallel bit, we just look at this node and use, first of all, use the Kirchhoff's current law at this point.
Let me rephrase my issue. So we replaced the resistor, we placed the capacitor in the feedback line. But here we have put it in the input.
The inductor.
Inductor.
Yeah.
Why not?
It's
is that the way it works, or
this is an exercise. So I'm not going to say much. I wanted to say something. Still do the IL, for example. This is IR. New exercise, and do the node equation and see what you can get as VR. So it's not that we put this now at this point. The idea is, if we wanted to act as an integrator, this is what will be able to give us as an integrator. Otherwise, it will be. We shall see. For the case of the differentiator, instead it is the reverse. Put the inductor the other side, and the resistor goes this other side. Because of the idea behind the V being the same as divide T, whichever way you want to define that, and the CV, when we are looking at the I, my issue is about the integrator in terms of where do we update it, how do we come up with the integral, and then the differentiator, the DDT. When we finish these ones, then we shall be able to reflect and see why this one is called the differentiator, the other one is an integrator. But this is just, we are just trying to look at the different circuit organizations of an op-amp, how are the different circuits. Then application of these op-amps is what will make sense most. Okay, see you in the afternoon.